Okay, graphing with derivatives. We're going to put everything that we've done with the first derivative, the second derivative together here, and pretty much turn ourselves into a human graphing calculator. It's going to be amazing. So, we are just going to start with an example here. Y is equal to x over 1 plus x squared. And our goal is to find out what the graph of this thing looks like and graph it. So, first things first. Without knowing any calculus at all, we're going to want to find the domain, the range, the x-intercepts. Okay, there we go. The y-intercepts. Put these little dots in here. Any vertical asymptotes that might be there, horizontal asymptotes if they've got them, any holes, any symmetry, and the end behavior is going to be important. So, and B, there we go. And these are things that you learned hopefully last year in pre-calculus, and you can find them for any function. So, domain. We mentioned domain. If you don't remember domain, take a look at the pre-calculus stuff, but essentially, I say essentially a lot, I know, I'm sorry. Pretty much what we're looking for is what can't x be? And there's three things we can't do. We cannot divide by 0, which means the denominator cannot be 0. So 1 plus x squared cannot be 0. So we can check this out. Doesn't equal 0. Well, that means x squared cannot be negative 1. And that never happens anyway. X squared never equals negative 1. So we're never dividing by 0. So that's good. We also cannot take the square root of a negative number, which there's no square roots in this function, so we're not worried about that. We also cannot take logs of anything but positive numbers. And nothing like that's in there. So the domain of this thing, very nicely, is all real numbers. The range you probably didn't spend too much time finding last year because range is hard. We're actually not going to write down what the range is until we graph this thing. So we'll come back to that later. X-intercepts happen when y is 0. So you set this thing equal to 0. And you solve for x. Now the only place a fraction can be 0 is if the top is 0. So this equation breaks down into this, and there we go. X equals 0 is our x-intercept. So that's 0, 0. Y-intercepts happen when x is 0, so you plug in 0 and you get 0 again. So if a function goes to the origin, that's the y-intercept. Vertical asymptotes, well, if your domain is all real numbers, there can't be any vertical asymptotes. But we'll do some examples with vertical asymptotes. You find those by finding where the denominator is 0 while the numerator is not 0. That's not happening in here. The denominator can never be 0. Horizontal asymptotes, you remember if it's a fraction like this, all we're looking at is the degree of the top, the numerator, and the degree of the bottom, the denominator. If the degree of the bottom is bigger, then the horizontal asymptote is y equals 0. Okay? And since the degree of the bottom of ours is bigger, that's a horizontal asymptote. If the degrees are the same, then it's the fraction of the coefficients, and if the top is bigger, there is no horizontal asymptote. Holes, in this case, there are none because the denominator cannot be 0. Symmetry. To find symmetry, you plug in negative x for x. So I'm going to rewrite this as negative x over 1 plus negative x squared. And notice how I put it in parentheses. And we're going to see what this simplifies down to. Well, it's negative x over 1 plus x squared, which is the same thing as the negative of x over 1 plus x squared. Well, if you plug in negative x and get the negative of the original, x over 1 plus x squared, that's an odd function. And the end behavior, well, end behavior, you only got a few options. They could both be up, they could be down, one could be down, one could be up, or it could be flat like a horizontal asymptote. And we have a horizontal asymptote, so the end behavior in this case, I'm just going to put like this. On both ends, it's just flat. That's all of our pre-calculus stuff. Sometimes it involves a little bit of work, but not too bad here. We'll find the range later. Now we're going to find the calculus stuff. And what I usually make the kids find are the critical numbers, the intervals of increasing, the intervals of decreasing, the relative max, and any relative mins. So we're going to do this. Okay, I don't like putting dashes. I don't know why I just did that. Dashes look like negatives sometimes, and it always confuses me. And I'm easily confused, so I try to avoid it as much as possible. But every single one of these things is going to come from the derivative, y prime. So we're going to drive this thing and use that to find critical numbers and increasing, decreasing, max, min. So let's derive it. Y prime, we're going to use the quotient rule. This is where our calc comes in handy. Quotient rule, derive the top is 1 times the bottom. That's 1 plus x squared minus the top x times the derivative of the bottom, 2x. All of that is over the bottom squared. 1 plus x squared. Now we just got to put all this stuff together. Don't cancel these things out. We've been through too much together here. You cannot cancel those. 1 plus x squared will not cancel with 1 plus x squared because there's a big minus up here and you'd have to cancel it on both. Remember, one big fraction bar is like the distributive property. There you go. Brain fart. Distributive property. So to cancel this out, you'd have to be able to divide it into this part on the right and this part on the left. And it doesn't divide into the part on the, I said that backwards. This part on the right doesn't divide. Anyway, we're going to simplify. And we simplify just by multiplying everything out and putting everything we can together. So this is going to become minus 2x squared over 1 plus x squared still. And simplifying further, we get plus x squared minus 2x squared is 1 minus x squared over 1 plus x squared. There we go. And I'm going to erase this here. What we're left with, you're not really done simplifying until you factor it as much as you can. So let's factor the top. That's 1 minus x, 1 plus x. And the bottom does not factor. 1 plus x squared doesn't factor. So it's 1 plus x squared. All right. Now, we want to find our critical numbers. So let's do that. Get out of here. Well, the critical numbers happen where this thing is 0 or undefined. So it equals 0 when the top is 0. And that is at x equals 1, x equals negative 1. It's undefined where the denominator would be 0, and that never happens. We realized that back here in the original. 1 plus x squared is never 0, so it's never undefined. It's no problem. Now, define increasing, decreasing, max and min, we make our y prime number line. There we go. And you put our critical numbers on there. Negative 1 and 1. And put y prime on here so you know what this number line represents. It's the y prime, that's what we're checking. Now, since our derivative is all factored out here, this finding out when it's positive and negative is very simple. I'm just going to pick a number less than negative 1, like negative 10, plug it in, and see what this whole fraction turns into. Well, when I plug in negative 10, I don't care what number I get. I just care if it's positive or negative. So 1 minus negative 10 is a positive number. So we have a positive times 1 plus negative 10 is a negative number. And the bottom is squared out here, so it's always positive. No matter what you plug in here, if you square it, it's going to be positive. So positive. So we're going to get a positive number times a negative number divided by a positive number. That is a negative number. The first derivative is negative, meaning that, come on, get out of here, parentheses. Our function is decreasing on this interval. I'm going to plug in a number between negative 1 and 1. 0, easy enough. When you plug in 0, you're going to get 1 times 1 over 1. That's positive, meaning my function is increasing on that interval. Plug in a number bigger than 1, I'll pick 10. You plug in 10, you get 1 minus 10 is a negative number times 1 plus 10 is a positive number divided by a positive number. That's negative. The function's decreasing then. And you can kind of do that in your head. If you want, you can plug your number in and do all the math and find the actual value you're going to get, but it doesn't matter. And the reason why we need to check one point here is because we know that the derivative is never going to change sign at any value less than negative 1, because if it did, we would have found it as a critical number. So increasing is between negative 1 and 1. Decreasing is from negative infinity to negative 1, union with 1 to infinity. And we have max and min here. Since the function goes from decreasing to increasing, down to up, that's a minimum at negative 1. So the x value is negative 1, and we want the y value. So we plug negative 1 into the function. Negative 1 over 1 plus 1 is 1/2. That's the minimum. If the function goes from increasing to decreasing, that goes up and then down, that's a maximum at positive 1. You plug in 1 and you get 1/2. Excellent. 1/2. Right, I did that wrong. This is negative 1/2, I'm sorry. Because negative 1 over 1 plus 1 is negative 1/2. Now, the reason I knew that, I just checked myself. Oh, man, you don't go here. The reason I knew that is because I checked my symmetry. This is an odd function. And since it's an odd, not odd like, you know, probably you are. You're probably you're a weirdo. Looking at math videos, weirdo. I don't think my jokes are funny at all. I'm sorry. Odd means that at opposite x values, like 1 and -1, the y value should also be opposite. 1/2 and -1/2. Okay, I had +1/2 here. I knew that was wrong. So that's just why symmetry is kind of nice to know sometimes. All right, so that was our first derivative. That found all that junk. Oh man, I just erased it. Crap. I need to know what it is. What was that? 1 minus x squared over 1 plus x squared. There we go. Because we got to find the second derivative to find what's coming up next, which is concave up, concave down, and inflection points, or points of inflection. And this is what I make my kids do for every single problem. It's a lot of work, but it's just putting all the calculus we know together. Just following this precise pattern here.